Hi, today we are going to discuss about traveling wave tube. As we discussed already, klystron and two cavity klystron and reflex klystron tubes. That is also one of the types from microwave tubes, and this is the second type, traveling wave tube. So, what is traveling wave tube? What is the purpose of this traveling wave tube, and why it is used, and what is the applications, advantages, and disadvantages, and working principle? We will discuss in the upcoming slides. So, in the traveling wave tube is a higher power amplifier used for the amplification of microwave signals up to wide range. It is a special type of vacuum tube that offers an operating frequency ranging from 300 MHz to 50 GHz. So, these tubes are non-resonant structures that offer continuous interaction of applied RF field with the electron beam over the entire length of the tube. Because of this reason, it provides wider operating bandwidth. So, this concept is based on the majority number of traveling wave tubes. So the traveling wave tubes are used in the form of TWT, and it is majorly used in the amplification of RF signals. Basically, a traveling wave tube is nothing but an elongated vacuum tube that allows the movement of electron beam inside it by the action of applied RF input. So the movement of an electron inside the tube permits the amplification of applied RF input, as it offers amplification to a wide range of frequency. This is considered more advantageous for microwave applications than other tubes, and it offers average power gain of around 60 dB. So the output power lies in the range of few watts to several megawatts. And a traveling wave tube is basically of two types. One is helix type and the other is coupled cavity. And this construction of traveling wave tube is, we will study from this diagram. So the helical traveling tube consists of an electron gun and a slow wave structure. The electron gun produces a narrow beam of the electron. A focusing plate is used that focuses the electron beam inside the tube, and a positive potential is provided to the coil helix with respect to the cathode terminal, while the collector is more positive than the coil helix in order to restrict beam spreading inside the tube. A DC magnetic field is applied between the traveling path by the help of magnets. The signal which is needed to be amplified is provided at one of the ends of the helix, present adjacent to the electron gun, while the amplified signal is achieved at the opposite end of the helix. So, from this figure, we can clearly see that attenuator is present along both the sides of the traveling wave tube. This is so because traveling wave amplifiers are high gain devices. So, in case of poor load matching conditions, oscillations get built up inside the tube due to reflection. Thus, in order to restrict the generation of oscillations inside the tube, attenuators are used. And these attenuators are basically formed by providing a metallic coating over the surface of the glass tube, and need of this slow wave structure. So we know that the velocity of the electromagnetic wave is very much higher when compared with the phase velocity of the electron beam emitted by the electron gun. Basically, the RF wave applied at the input of TWT propagates with the speed of light. So the speed of light is 3 into 10 to the power 8 meter per second. While the propagation velocity of the electron beam inside the tube is comparatively smaller than the velocity of the RF wave. So if we try to somehow accelerate the velocity of the electron beam, then it can be accelerated only to a fraction of velocity of light. So it is better to reduce the velocity of the applied RF input in order to match the velocity of the electron beam. Therefore, a slow wave structure is used that causes a reduction in the phase velocity of the RF wave inside the traveling wave tube. The slow wave structures can be of different types, like a single helix, double helix, zigzag line, corrugated, coupled cavity, or ring bar type. So a single helix slow wave structure is formed by wounding a wire of element like tungsten and molybdenum in the form of a coil. So the helical shape of the structure slows the velocity of the wave traveling along its axis to a fraction of about 1/10 of c. So this is because due to the helical shape of the structure, the wave travels a much larger distance than the distance traveled by the beam inside the tube. So in this way, the speed of wave propagation depends on the number of turns or diameter of the turns. So more specifically, we can say that change in pitch can vary the speed of propagation inside the tube. So this equation given below shows the relation of phase velocity of the wave with the pitch of the helix. So that is Vp equal to Cp divided by root of p square plus pi d the whole square. So c equal to velocity of light, Vp is the phase velocity in meter per second, p is the pitch of helix in meter, and d is the diameter of the helix in meter. So therefore, this causes continuous interaction between the r of input wave and the electron beam, as the velocity of propagation of the two is not highly different. As such, interaction is the basics for working of TWT. Thus, slow wave structures are used. So, till now we have discussed the complete constructional structure of TWT. Let us now understand how the signal gets amplified while traveling inside the tube. So, the applied RF signal produces an electric field inside the tube. Due to the applied positive half, the moving electron beam experiences accelerative force. However, the negative half of the input applies a decelerative force on the moving electrons. This is said to be velocity modulation because the electrons of the beam are experiencing different velocity inside the tube. However, the slowly traveling wave inside the tube exhibits continuous interaction within the electron beam. So due to the continuous interaction, the electrons moving with a higher velocity transfers their energy to the wave inside the tube and thus slow down. So with the rise in the amplitude of the wave, the velocity of electrons reduces, and this causes bunching of electrons inside the tube. The growing amplitude of the wave resultantly causes more bunching of electrons while reaching the end from the beginning, thereby causing further amplification of the RF wave inside the tube. More specifically, we can say that forward progression of the field along the axis of the tube gives rise to amplification of the RF wave. Thus, at the end of the tube, an amplified signal is achieved. The positive potential provided at the other end causes collection of electron bunch at the collector. The magnetic field inside the tube restricts the spreading of the beam as the electrons possesses repulsive nature. And however, as the TWT is the bidirectional device, so the reflected signal causes oscillations inside the tube, but as we have already discussed earlier, that the presence of attenuators reduces the generation of oscillations due to reflected back wave. So sometimes despite using attenuators, internal impedance terminals are used that puts less lossy effects on the forward signal. Next, we are going to discuss about applications of traveling wave tube. So it is used in continuous wave radar systems and broadband receivers or of amplification, and to get higher power output in satellite transponders. So from the above discussion, we can conclude that no resonance structure is present in the interaction space. This provides amplification up to a wide bandwidth operating range. However, the input and output coupling arrangements must be considered carefully as they limit the operating range.